Hi, my name is Adam Ress, and this is my presentation on Lab 6, Magnetic Molasses. Introduction. The purpose of this lab is to study magnetic induction and induced currents by observing a bar magnet falling through an aluminum tube and comparing its motion with predictions from computational models. A preview of our results shows that we recorded an average time of 0.47 seconds for the magnet to fall through the tube, and our computer calculated 0.31 seconds. So some fundamental principles to know before we dive deeper is Biot-Savart's law, which relates the magnetic field at a point to tiny currents with the help of the vector cross product. We also have Faraday's law, which is very important. And Faraday's law tells us that when there's a change in magnetic flux, this results in the creation of a electromotive force to counteract the change in flux. And then it's also important to know Newton's second and third laws. F the net force equals mass times acceleration, and for every action, there is an equal and opposite reaction. So now for the experiment itself. So the experiment was to drop a bar magnet through an aluminum tube and to time how long it took to fall. So the components was the bar magnet, the aluminum tube, and the stopwatch. And the system was the bar magnet and the aluminum tube, and the surroundings was everything else. So the idea is that when the bar magnet falls at the different points, um, the magnetic field is going to change, which will then change the magnetic flux, and it will cause these induced currents above and below the magnet, which should theoretically slow it down. So we drop the magnet through the tube, and you can actually hear that the magnet is touching the sides, which might actually cause a little bit of problems. But anyways, we still record our results. So the mass of the magnet was 0.023 kilograms. The magnetic dipole moment of the magnet was 1.5 ampere meters squared. And then the data for the aluminum tube is that the length we calculated as zero point 0.4 meters. The thickness was 0.002 meters. The inner radius was 0.02 meters, and the outer radius was 0.022 meters. And so we did 5 trials of this, and we got that the average time was 0.474 seconds. So now we have to put this into GlowScript. So we have all our initial conditions in GlowScript, um, all of the data that we calculated, and now we're going to see if it was the same. So here's the visual of the GlowScript program running. So I slowed it down so we can see it. So you see the magnet falling, and you can see the induced currents that are creating a force that acts on the magnet to counteract the gravity force. And so you can see that in GlowScript, we calculated that the time for it to fall was 0.31 seconds. So now for the discussion. So the differences between the real life and computer simulation. So the experiment time, we calculated an average of 0.47 seconds, and the computational time was 0.31 seconds. So definitely it was pretty close, but the computer did think it was faster. Some assumptions that we made for the computer simulation was that the bar magnet acted as a magnetic dipole. We did this so we could apply Biot-Savart's law. We also assumed that the only forces in play were the magnetic and gravitational forces, and that there were no external forces, and that air resistance was negligible. So some potential errors is that the electronic and magnetic devices in the surroundings could have affected the forces on the magnet. And so one example of this, so the friction against the sides of the tube as the magnet was falling and touching the side. So that's an external force that we didn't account for in the computer simulation, but definitely could have affected um, the time. And then also human error, inconsistent magnet dropping, different orientations, or even the stopwatch timing. We weren't super accurate with that. So now for the discussion question. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So if the resistivity approaches zero, the induced currents in the conductor would become extremely large, generating a magnetic force that would almost just strong enough to effectively counteract gravity. This would cause the magnet to fall incredibly slowly, and it would just appear to be almost just levitating or floating. The next question is, what if there were holes cut into the tube or slots? How would this affect the ring currents in your model? So the holes cut out would prevent the current from flowing in a ring in certain places. Overall, this would make the magnetic force much weaker, so the magnet would not be slowed down as much as it would otherwise. Thanks for listening.